Yeah, thank you, Joshua, for reminding me. Now the lecture is starting to be recorded. And let's just quickly review what we have been talking about last time. Last time, we talked about procedure call. We mentioned when we have the C program, we can do arithmetic operations, we can do um, control flow, and we can do many things. The reason we can do it from our class perspective is because the assembly language supports such functionality as well. We talk about how to do the control flow using assembly. Basically, we have three pieces. The first piece is arithmetic operations or compare or test. These instructions set the conditional code. So the conditional code is the second piece. The third piece usually is the conditional jump, checking the conditional codes, either make the jump or not. By such three elements, we can make the control flow happen in assembly. That's the reason we, in the C program, we can still do the control flow because assembly supports such functionality. And here, we talk about the procedure call. We can have the procedure call in our C program. The reason from our class perspective is the assembly language also supports procedure call. And we already talked about for the procedure call, the reason to have such a functionality in C is to modularize the programs so that instead of write a giant big piece of program, right now we can break it down to many small pieces and assemble them for convenience. So we talked about assembly, how to make procedure call in assembly. Here is a sketch about what does a procedure call look like, and for this procedure call, you can see one piece of them is call, C-A-L-L. And for the call, we have target address. In here, it's a level func integer, so that we can jump to the caller, so calling function after it. And we raised two questions. When we make the function call, we have to jump from the main function to the callee function. And the first question is, when callee finishes its program, how it jumps back to main function? Where jump back to? This is the first question. And then the second question is, when we have function call, we usually takes in some parameters filled by the caller, and then these parameters would be passed to the callee. And the question is, how the parameters could be passed to the callee? This is the second question. We talk about these two questions. For the caller, in our example, is main function. It knows the exact answers. Where to jump back? It is the address of next instruction after call. So in our case, it is the instruction. Let me see. It is instruction right here. Here gonna be the place we jump back to. So caller knows the answer for the first question. The second question, how to pass parameters. For the parameters, caller also know it because that's what the caller gives to the callee. So it seems like the caller knows the answers of these two questions. The question is how the caller can let the callee know the answers so that the callee can receive the parameters at first, and then after finishing the codes, it can jump back to the right location. So we talk about we generalize this problem as how the caller tells callee what is the answers for these two questions. And we review it again. We propose something called a stack. Stack is a piece of memory first. It is in our memory. And the stack is also adopts the stack data structure. The last in, first out. We give the analogy. It's just like the laundry basket. You put in red, blue, black coats, and then the first coats you get out should be black, then blue, then red. So this is the order given by the stack structure. It adopts the stack structure, but also it kind of it's a real physical memory existing in the RAM. And this stack is used as a medium for the caller to tell caller. And on this stack, you can see we have several parameters. We have the return address. Apparently, this is put down by the caller, and the caller can know what is the return address. This is the first one to answer the first question. And also, you can see we have the argument 7 to n. This is a place we can put down the parameters by the caller, so that the caller can check these parameters and receive them. And we mentioned about that for these parameters, the 64-bit machine, we introduce extra 6 registers to pass the parameters, working along with the stack. So the 6 registers would receive the first 6 parameters, and then if we have more than 6, we put on the stack. This is current mechanism for the 64-bit machine. Before 64-bit machine, we only use stack. We don't have these 6 registers to help the stack about the task. And we give you a control flow when we make a function call, what happens back of the stage. We introduce, here is a RIP instruction pointer. Whatever number, whatever address have in RIP, and then this address is the is holding the instruction we're gonna execute when we do it. And then we have a stack pointer. For the stack pointer, always points to the top of the stack. Right now, the top of stack, we have been given the arrow pointing to the top of stack. So less intuitively, our stack is upside down. So the bottom in this slice is the upper edge of this big square. The lower bottom actually is the top. So our stack is upside down. Less intuitive, but that's what happens in our memory. And the stack pointer points to the top of the stack. It tells us when we add an item into the stack, where we're gonna put the item. And we give the example. We make a function call, and you can see the instruction have the address 400563, and this is exact same address for the RIP. That's why we execute this instruction, because its address is given in the RIP. When we do this function call, there are several things to happen. First of all, the caller would push the return address. The return address is right here. We'll push this return address on the top of the stack. This is the way caller tells caller what is the return address. So we push this return address on it. We see it, and because we push item on the stack, apparently we need to update the stack pointer by lowering it. You remember we talked about this is a reverse process. When we try to increase or grow the stack, actually we decrease its address. Stack pointer right now it's ending with 40 because the address is 8 bytes in our example. So we need 8 bytes more space for the stack. Instead of adding 8, we minus 8. That's the way we grow our stack. So we minus 8, makes this number end with 38. Now we can see the new top of the stack. So that when we add something on the stack, we need to subtract a number from the stack pointer. And here we see the top of the stack. And at the same time, we give the address of the callee, which is 400540. This is the address for callee function. We need to jump back to. So we give 400540 to the RIP, so that next cycle, when CPU wake up again, it will find 400540, find the address, and we'll look what is the instruction. In our example, it's push. Then we would execute the push instruction. This finished the first half of function call. The next part is how we jump back. Let's see, we do 400540. We do the push, finish this one. Then we will do the next one, 400541. At this address, we do the move RDX. Right? We do this, and when we finish all the callee's codes, we would do 4054D, which is RETQ, return. When we do return, it would finish the second half of the function call. That is how to jump back. In this example, we talk about, first of all, we need to find out what should be the return address. You remember return address, we give that on stack. So you can see the callee can go to the stack, find the return address, which is 400568, and then pop this return address to initialize RIP, instruction pointer. By doing so, we find where we should return to. And at the same time, we no longer need the return address. What do? We delete them. And how we delete it? We just update the stack pointer. You see this? The stack pointer, if we want to delete it, we add the size. The size is 8 bytes. So we add 8 bytes to delete it. And the outcome of doing so is we move the stack pointer upper one level. Our stack is shrinked by 8 bytes. And because right now stack pointer points to the new place, the older place holding 400568, this space would be regarded as empty by our system. We didn't bother to zero out this space because it takes time, take energy. We don't want to waste it, so we just leave it there. We talk about that's also the reason why we try to delete something. Actually, we didn't. We just move the pointer somewhere and regard the space to be empty. But actually, if you really take a closer look into the space, it still have the data. So that's why when you accidentally delete something, you can bring your disk to the technician, and then they may restore your data. And when you try to sell your electronic discs, phones, and then enter the store, they would do a complete removal of your data. And in that case, it takes a longer time, and they would zero out your storage. Anyway, so we deleted the return address. Next cycle, because we already updated the instruction pointer 568, so we just move the pointer to 568. And then we finish the function call. So the first half, we make the function call, jump to the callee. The second half, completed the callee codes. And then when we hit return, we find what is the return address, and then we jump back to where we are. This is the control transfer. And also we talk about how to pass parameters. We have 6 registers. RDI always have the first parameter. RSI always the second, so on and so on. We have 6 of them to pass the first 6 parameters. If we have more than 6, we would put that on our stack. And the return value, we always put in the RAX. That's the reason when we make a return in C, we just have one parameter, one variable we can return. You don't encounter a case you return several parameters or several variables. The reason is we only have one RAX. If you want to return a larger data, probably you have to use pointers. You can return pointers, and then the caller can use pointers to find the bunch of the data. But yeah, in terms of variable, we just return one variable. That's the reason why we just have one variable, because we just have one registers. That's also a very good example. What we can do in C should be supported in assembly. If let's say right now we want to revise the C program, we want to return 10 variables at the same time in the C function call. Can we do it? Probably not. The assembly only have one place to hold the return value, which is RAX. If we want to return 10, probably we need to redesign our architecture and assembly codes. We need to maybe bring another 9 registers on board in order to do so. So you can see the nice consistency between the C function and the assembly function. What a C can do should be supported by assembly as well. Okay, so return value, just the one place, RAX. And again, we mentioned this is a 64-bit machine case. It has been the latest update on the mechanism. If we talk about 32-bit machine, we don't use registers. We put all the parameters on the stack. And here's an example how we pass parameters. We write an example function call, pass, and we give 8 parameters. As expected, we should pass the first 6 parameters by registers, and the last 2 parameters on the stack. And the right side is assembly code we talked about, it is just trying to set up the parameters to be passed. If we rated the parameter here, we move the first number 1, this is the first parameter, into EDI or RDI. This is to pass the first parameters. And then second parameter, third, fourth, fifth, sixth. So that's the way we pass parameters. We just put the value in each corresponding registers, and then the callee would come to find it by the predetermined order. And if we talk about if we have more, we would put that on the stack. And in this example, I believe this is the last example we talked about last time. So this is a function call, and we're trying to look at what should be the layout of the stack. Right? Should be layout of the stack. And it is, for this one, most of it is trying to calculate the offset or the addresses. So as long as you can find out the addresses and figure out the order of the address, then you should be able to do that. Again, because of the limitation of the space, we assume each slot right now is 8 bytes. From the left side to the right side, let's see. Yeah. We talk about here for the 8 bytes. For the 8 bytes, we can divide the space into 8 subslots. 1, 2, 3, 4, 5, 6, 7, 8. And we assume the leftmost have the smallest address, we think, right? So you can imagine if here is a 0, there'll be 1, 2, 3, 4, 5, 6, 7. We just assume this kind of address. Actually, it's not proper. Okay, let me do this. The question, when will these slides get put on Piazza? I will try to put that on Piazza during this weekend. Again, let's assume we have 8 slots, and from the left side, this is smallest guy, and to the right side, this is the largest address. By figuring out the address, then we can do the find in place code the parameters. Let's now we finish the review. Is there any questions? Okay, let's introduce some new material. Okay. We have local variables. Where are we gonna put the local variables? That's the question. In the for the local variables, we have 2 possible places to hold it. One is the registers. Apparently, registers. We can have 16 registers in total. Then it could be a place we hold our local variables. But how about if we have more than 16 registers? So we need to come to the memory just in case we have so many local variables. And yes, it can happen. You already see many cases that we put the local variables in our memory. To be particular, which piece of the memory we hold this local variable? It's on the stack. For the stack, we talked about it. It is used as a communication channel. It's a way that a caller tells Kali what is the return address, first piece of information, and the second piece of information is what is the past parameters. It turned out our stack can be used for other purposes as well. That is to store the local variable. So if you interpret the stack, and then you will find that the stack have many frames. And when we make a function call, we just switch the execution to the callee. At the same time, the callee would start to use the stack as a way to store local variables. Here's the example. We have the function func, and we give 4 local variables and return 10. And in my example, it is used it is using the stack as a way to store the local variables. The first step, which is to push the RBP on the stack, that is to preserve the RBP of the caller. We don't want to destroy the value inside of it. When we return, we want to restore the RBP, which happens here. So if you look at the RBP, this place, we just want to preserve the RBP of the caller. And here you see we pop RBP. This is to restore the original value. In between, we would use RBP to be the callee's RBP. Okay. For the RBP, we push that into the stack that is belonged to the caller. And then we move the RSP to RBP. This is a way to initialize the callee's RBP base pointer. And then we need to set up 4 local variables. And we chose the stack to be the place to hold the local variables. First of all, we use RBP as a baseline, and I use the offset to find the right location to hold it. Here, we move number 1 into RBP -4. We talk about RBP right now is pointing to the slots right here. If we want a -4, if we want a -4, that is to be here. And when we move number 2 to the RBP -6, and then we would move the numbers right here. And at the same time, if we want to move the 3-1 into RBP -7, and then we put it right here, 3-1. And then finally, if we look at RBP -10, we will give it right here, 3-4. So you can see here, we use the RBP as a baseline and have the offset to find the right locations on the stack to store the value. And that's also happened in our previous example. So when we find the memory, find the local variables, you usually see these parentheses. That means the memory location, and inside of it, it usually is RBP. That is we using the space of the stack, and then we just use the offset to find the right locations to hold it. Okay. Here's the local variables. And the local variables, in short, it can be put into the stack, or it can be put into the registers. The next part, we would explain the callee saved registers and the caller saved registers. And for the callee saved, so the basic idea coming from this callee and caller saved registers is when we make function call, we only have 16 registers. The caller and the callee would share these 16 registers. Let's see, caller uses register RBX, RBX is used by the caller. And then when you make the function call, it could be possible that a callee can also use the RBX. Apparently, there is a potential confliction when two parties, caller and callee, they share the same set of registers. If caller uses RBX and a callee uses RBX as well, one case is the callee could mess up the value inside of the RBX. When we make the function call, and the caller would never see the same values in the RBX. And so this would just create a conflicting outcomes when caller and callee share the same set of registers. Apparently, we need to design some rules and standards how the two parties can share the resources. And based on how to share, we have two ways to use. One is called the callee saved registers. For the callee saved registers, one example is RBP. Let's look back at the previous example. When the callee wants to set up its own base pointer right here, it has to save the caller's one. This is trying to save the caller's one. So we call this kind of register callee saved registers. That is, callee preserve the registers so that these registers have unchanged values after return. So callee needs to save the registers. In other words, the caller claims the priority over using these registers. The example is RBP. RBP caller have its own base pointer. Callee wants to use this base pointer. Before callee use it, callee have to save it. That's a push queue RBP comes from. And when callee is one step from returning, it has to pop RBP. This step is to restore caller's RBP. And the one step from returning, it restores the original value of RBP, makes this RBP again to be the caller's base pointer. By this way, you can imagine when caller again find the RBP base pointer, get the return from the callee, the RBP would be the same. So we call this kind of parameters callee saved registers. And the second case we call the caller saved registers. It assumes the caller doesn't have the priority. The callee and the caller have the equal rights over using the registers. And in such case, if caller wants to preserve, if caller wants to preserve the value in a register, then caller has to save it. Otherwise, the callee could use the registers, change the value of it, and then caller would lose the data. So it's caller's job if caller want to have the same kind of value inside of registers. So we call this caller saved registers. And in this case, we assume caller and the callee are equal. And in the previous case, callee saved registers, caller have larger priority than callee. So if callee wants to use registers, it has to keep the value and restore it before return, because caller have the priority. It's a callee's responsibility to keep the value intact after function call. But in the second case, caller saved registers, they are equal. there's no one should do favor for another one. So the caller, if want to see the same value after function call, it has to preserve the value and restore the value after function call. Is there any questions? Okay. This is the calling saved registers and the caller saved registers. Here is the example about the function call. And for this function call, I will not okay. In this function call, we have the assembly code at the left hand side, and the right side, which is the layout, what is the stack look like when we move through these functions. And I will give you 5 minutes. You can read through this assembly code and look at the stack and trying to figure out what is the kind of function call we have in this place. I'll give you 5 minutes.
Professor, can you keep the slide back up? We don't have the slides, so.
Oh, sorry. Yeah. Okay. There we go.
Thank you.
And no problem. 5 minutes. Okay, let's do it together. Do you have any clue about what kind of this function call is?
Is it some kind of recursive?
Yeah, that's right. Great. That's a recursive function call. Let's look at it and why this is recursive. So first of all, let's look at the main function. Here's the main function. And when we execute call Q, we find that the target address is 464A. And let's look at where is 464A. So we find the callee. There is a callee function. And we talk about when we make the function call, we would push the address of next instruction, 4691. This should be the return address on the stack. So here is the return address. Is there any questions? Okay, this is return address, and we push the return address on the stack, and then we make the function call. When we do the function call, first of all, we push RBP on the stack. We talk about this. Here, it's a callee saved register. It is callee saved register. And we moved RSP to RBP. This is the routing to set up the callee's base pointer. And then here we subtract RSP by 10. So we can note here our RSP was here. It's pointing to the slot right here. We talk about we have 8 subslots. The leftmost is the smallest guy. So the leftmost have the address, and this address is where the RSP is pointing to. And then we move the EDI into RBP -4. There is, oh, sorry. So we subtract 10 from RSP. If we subtract 10, that is 16 in decimal. We would go from here, 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 until here. Here, this place is RSP -8. Is there any questions? And if we want to RSP -16, we come to here. This should be RSP -16. So after subtract 10 from RSP, what the outcome is, we actually move the RSP to the place right here. Let me change the color. This would be the new RSP. By this way, we open up more spaces on the stack. Next step, we look at here. We move the EDI into RBP -4. RBP, let me update RBP. RBP should be here as well, because it was equal to RSP. And now RBP -4. So this is the smallest address within the slot. If RBP -1, we would go here. this subslot is the largest among this frame or this slot. If RBP minus 1, we go here. RBP minus 2, we go here. If minus 3, here. Minus 4, we come here. Here is RBP minus 4. And now we move EDI into RBP minus 4. So we would occupy the slots right here to hold number 2. Why it is 2, we can look at the codes right here. We move 2 to RBP minus 8, and then move RBP minus 8 to EAX, and move EAX to EDI. So the EDI is having number 2 inside at the very beginning. So we move 2 out of the space. Is there any questions? Why we place number 2 at such a place? Okay. Yeah, I find maybe some of you not sure how we calculate the addresses on the stack, right? Yes, let's spend some time talking about this. Let me open a new slide. Okay, let's talk about how to do the calculation on the stack. Which is the given example. And let's just have a fixed size of stack. Let's assume each slot right now is 8 bytes. And each slot, we have 8 subslots. One subslot is 1 byte. And let's see how we can do the calculation. Let's see, we want to start from 0. So in real example, we don't have an address like that. But let's just keep this example small. 0, 1, 2, 3, 4. No. This is try to prevent some confusion. Okay, let's write down here. We use green to denote the address. Let's start from 0. This slot have the address 0, 1, 2, 3, 4, 5, 6, 7. Okay. And if we look at the upper slot, we talk about the upper slot. It should have a higher address. And in this case, we would start from 8. So we would say the address of the leftmost subslot is 8, 9, 10, 11, 12, 13, 14, 15. So this guy would have 15. If we continue to list the subslot at the third slot. And now we would have address here. What should be the address here? Any idea?
16.
Yeah, that's right, 16. We would have 16 right here, 17, 18, 19, 20, 21, 22, 23. So here would be 23. Here is an example about how we address the subslots. So you can see the leftmost subslot always have the smaller address, and the rightmost subslot have the higher address. So if we go through from 0 to 7, 8 to 15, 16 to 23, it looks like this. And at the other side, let me draw what it usually look like in our stack. Let's see, here is I use the gray as a stack. Now I still draw something here. And unsurprisingly, we still have this 8 subslot, 3, 4, 5, 6, 7. We still have this 8 subslot, leftmost smallest address. We still follow the same routine. And usually, you would see something like RBP stack pointer points to this stack. What we usually do is we find the address of the leftmost subslot, and this is the address given to RBP. It's the top of the stack. You remember, it's not top of the stack. So when we talk about RBP, we usually have the leftmost subslot and find the address, and then we give this address to RBP. This is how to initialize the base pointer. Okay. And when we use RBP -4, in our case, we use RBP -4 to hold the number 2. And now we need to find where's RBP -4. So again, if RBP is 16, if we -4 is 12, it should be here, right? This is 15, 14, 13, 12. They're going to be here, right? If RBP.
We can't see the pointer, by the way. I can't.
You cannot see the pointer?
Yeah, it looks like it sounds like you're pointing to sections on the screen, but I can't see it.
Yeah, we can't see the mouse.
Oh, do you see the green dot right here?
Yeah, I can see the green dot, but
I see.
You can only when you actually mark it. I can't see like the mouse hovering over.
I see. Yeah. Thanks for reminding me. So here's the green dot. If we assume RBP equals to 16, right? Then RBP -4 would comes to this green dot, right? Or 12. In the similar way, you can imagine here is our RBP. Let me see. Or I can have the arrow laser pointer. Okay. Do you see the pointer? Laser pointer?
Yes.
Oh,
yes.
That's great. So if the RBP equals to 16, and then if we -4, we go to this green dot. And in our example, RBP right now, we don't know what exactly the number is, but what we know is if we minus 4, where are we gonna end up with? It will be here. Similar dot. Right? If we RBP is right here, minus 4, it comes to the green dot right here. Similar way. If you like, this is RBP. If we minus 1, we end up here. If we minus 2, here. 3, here. 4, right here. If you like to use 16 as example, here is 16. If you minus 1, you go to 15. Minus 2, go here. Minus 3, minus 4, end up with this green dot. So it's a similar way. Is that clear? Do you have any questions? If you have questions, feel free use your microphone or put in the questions in the chat window. Okay, one question from Roman is, in the original example, how did we get 2? Let's go back a little bit. The reason, let me clear it. Okay. I would in the original example, you can see here when we make the when we move EDI to the RBP minus 4, right? The question turns out to be, what's the value for EDI? If we check EDI, we have to go back to the main function. EDI is set up right here. It's move EAX, the number in the EAX, to EDI. And what is number for EAX? Let's look at the previous instruction. It's move the number from RBP minus 8 to EAX. What is RBP minus 8? We go back again. We move number 2 to the RBP minus 8. So we find the original number. We move number 2 through these chains of memory location and variables, and then we finally reach inside of the EDI. So after these 3 instructions, EDI would have number 2 inside. Did I answer your question? Okay, great. Another question from Nick. My main issue is keep track of what all the calls do and how read them. Yeah, that is pretty consuming. My suggestion is write down something, keep track. I know it's sometimes consuming, but that's the only way we can keep track of the things. Let's just right now, let's just try to give you an example. So here we talk about why we RBP minus 4. Why RBP minus 4? We finally find this spot. And then let's finish with the last step. We move number 2 inside of this RBP minus 4. And we talk about number 2 is EDI, which consumes 4 bytes. And for the 4 bytes, we use the smallest address to denote these 4 bytes. The smallest address is RBP minus 4. That's what is specified in the assembly. So finally, we would find the 4 bytes as here and put number 2 inside. So we put number 2. Oh, sorry. It's not so clear, this color. Eraser. Color. Let's put black here. This is where we put number 2. So again, we need 4 bytes. And what is the address of it? That address should be the smallest one. So the smallest one is RBP minus 4. Then we need RBP minus 3, 2, and 1 to altogether hold number 2. So, any questions so far? Why we have the right half of the slot to hold number 2? Okay. If you have questions, feel free to raise it out in the chat or use your microphone. Okay, so we solved one of the questions. Here we have, let's see, we have the RBP right here and RSP right here. So they equals to the leftmost subslot. Okay. Now let's do move the EDI into RBP minus 4. So here's RBP minus 4 somewhere here. There is RBP minus 4. It's right here. RBP minus 4. And we have the right half of the slot to contain number 2. Okay. Let's continue. After it, we compare the RBP minus 4, which is 2, with 0. Apparently, 2 is not equal to 0. So we would jump to 4662. We jump to 4662. Let's find where it is. 4662. In this place, we would move RBP minus 4. This is number 2 into EAX. Subtract 1 from EAX and move EAX to EDI. So EDI would end up with number 1. Is there any questions? Here EDI equals to 1. Okay, let's continue. EDI equals to 1. Here is something interesting to happen. We make the call, and the address is 464A. It's right here, 464A. It's right here. So it seems like we're within the function. We're calling the function itself again. This is a sign of a recursive function call. You know, when we make this function call, that's what happens in our stack. So first of all, we need to find the address of next instruction. 466F, right? This is the address of, this is a return address. So right now, the callee becomes the caller. This will be the return address. We have to put this 466F on the stack. We push this on the stack. It's right here. Okay. And we talked about when we put something on the stack, we need to update RSP as well. So after it, the RSP would point to the new top of stack. This is RSP. We have to do the things again. We need to go back to the first one. We need to put RBP on the stat again. We talk about this this instruction. It is callee saved instructions. It's trying to preserve the original RBP. So in this case, you can see when we push RBP on it, we have the RBP right here. It is the function one. It is function call, and it's the first time we make the call, right? We push the RBP on it. And then we follow the similar routine. We move the RDI into RBP -4 here because our EDI is changed to 1. So we have 1 here. And at the same time, we remember there should be a subtract for the RSP -10, 10. So it would end up someone here. That will be the new RSP. That will be the new RSP. For the new RSP, we still follow the routine. We compare the 1 with 0. It's not equal. Then we jump to 4662. And for the 4662, again, we subtract 1 from it. In this case, EDI would be 0. So here, EDI would be changed to 0. And then we make the function call again. We call 466A again. That's why we have another return address. And then we do the similar thing. But this time, on the stack, we put down 0 because EDI, we put down 0 because the EDI is 0 right now. And then from here, something began to change. If we have the 0 right here, let's see, we have 0. Okay, we do the compare. We find the RBP -4 is 0. We do the compare, and they're equal. So we won't jump, we stay. We move 0 into EAX, and we jump to 4676. 4676 is right here. We do a leave queue, and we return. It seems like we no longer do the recursive function call, and we exit the program. So and for the leave, you can see the leave is instruction for 2 instructions. We move EBP to ESP and then pop. So it's just in a single word, it's just a way to exit the function call. And you can see this is recursive function call. We call the same function. We call this same function 3 times. And here is a program, the corresponding C program for the assembly code. That's a much clearer picture. We give a variable A and make it equal to 2. As we see in the assembly, EDI is used to represent A. Then we make the function call. We keep track whether function call whether the parameter A would be 0. If it is 0, then we return 0. Otherwise, we would recurse. Sorry, for no reason, I mute myself. Yeah, let me go through it again. So we talk about if we follow the every step, and then we would find that this recursive function call made three rounds of recursive calls, and it's no different than normal function call, even though it is called a recursive call. But in terms of assembly and how assembly makes function call, there's no difference. You just repeatedly call the same routine again and again and again, and until you reach the ending condition. And if we look at the C program corresponding to it, here's the C program, variable A equals to 2. Apparently, in our assembly, EDI is representing variable A. We give number 2 to it, and then we make the function call first round. And then because A is equal to 2, then we would do a recursive call. We give A minus 1, which would be 1, given to func, and then do the function call again until the input variable A is equal to 0. Then we make the return. So this is a C program which is responsible for the assembly generated. Again, no difference, even though it's a recursive function call. In terms of call routine, it's the same. We just call the same function again and again. In terms of the stack, it just look like this. And here, this diagram is what I hope you to learn. And this is a piece of memory. We need to calculate the addresses so that we can find the right spot to hold the value. This skills is quite essential for our class and for the lecture later of the today. Okay, is there any questions? Okay, let's take 10 minutes break, and let's start to introduce the array and stuff in the second half of our class. Let's return 3:10. Okay, we'll get back to our class. Next, we will talk about array. Again, you can follow our thinking behind. We have the control flow, we have the procedure call for the C program, and also we have the array in a structure, these kind of variables in our C program. And let's see how the assembly implement it. In this section, we will talk about array, struct, and the union. In this, this is data structure, data type in our C program. Let's look at the assembly code that deal with it. Let's quickly review what is the array. We start with the example of array. So first of all, it has a type, and then we put the variable name. In our example, it's A, and then we give the size of the array. And if we put that in our memory, it should be something like the right side. And let's see how we translate each element into it. So first of all, we look at the size of T. T, again, this is the type of the array. Let's give you an example. Integer A, 10. Then the T in our example is an integer. If we look at the this memory layout, each element in the array right now have 4 bytes. It's 4 bytes. That is the size of integer. And if we look at the n, which is the size of the integer, sorry, the size of the array, then in our example, we should have 10 of them. We usually name this to be 0, A0, A1, A2, so on and so on. In our example, we should have 10 elements. We should end up with A9 in our example. And in the memory layout, we should also have 10 slots, and each one is 1 element, occupying 4 bytes. And in our memory, we use the continuous memory space to hold the overall array inside of it. That's the layout for the array. And when we only talk about A, the capital A, this is a pointer to the beginning of this table or list. That's what the memory layout looks like. Now, let's look at some examples, how we can calculate the address of it. I will do the first one. I will give you time to look at the second and the rest of the examples. We have, in the first example, we have char A, 12 elements. And let's try to fill out this table. Element size is what is the size for each element. Because this is the char string, each element is a char. So it will be 1 byte for each element. Start address is XA. Let's use this table as an example. XA is right here. This is the address for the start of the array. And you can see here should be A0, A1, A2, and then here should be XA plus 1, XA plus 2. The reason we plus 1 and 2 is because each element is 1 byte. If the char is 1 byte, so we just plus 1 in order to move to the next one. So A3, we would be XA plus 3, so on and so on. Element I, here is element I. How we can generalize the case, I could be 0, 1, 2, 3, or AI. Element I is, here is AI. What is the address for AI? So you can summarize it as XA plus, for example, I equal to 3, then the address of it, A3, is XA plus 3. So similarly, if we generalize the case, the element I, we can find the address of it to be XA plus I. This will be the address for element I. Is that clear? Any questions? Okay, let's continue. Now, let me give you some time trying to figure out what will be the answer for char star B8. Let me fill out the previous one. Size is 1, element is XA plus I. Okay, so I will give you 3 minutes. Try to fill out the second row. What should be the element size? And if we want to look at the element I, what should be its address? 3 minutes.
You're still muted.
Yeah, thank you, Luca. Yeah, what I'm saying is, so first of all, we need to look at what is the size for each element, or what is the type for each element. Then you figure out each element, the size of it. Then we are looking at the ith element. What should be the address of it for it? Feel free to give your answers in our chat window. So first of all, what is size for each element? Do you have the ideas? Roman, that's right. Let's do it together. For the set question, first of all, we see it's an array, and each of the array, let's put down here, is a pointer. It's a char pointer. We talk about for char pointer, it is about addresses. So for the 64-bit machine, the address is 64 bits, and then translate to the bytes, we have 8 bytes. So each element, we have 8 bytes. Put that here. This is 8 bytes. Now let's look at what should be the element i's address. We have the xb right here. This is the starting of the array. We want to find the ith element. Here, let me make it clear. There should be B1, B0, and it should be a char star, the char pointer, occupying 8 bytes. If we look at a B1, what will be the address for B1? Could you tell me? What is the address for B1?
XB plus 8.
XB plus A. Is there any other answers? So here, I will give you the clue. So each slot right now is 8 bytes because one element is a char pointer occupying 8 bytes. If we look at here, it's should something start with XB plus which number for B1? Okay, here, with the plus 8. Because here is the 8 bytes. XB is the very start of this array, and it should have the following 8 bytes. Following 8 bytes to hold B0. If we want to look at B1, we need to plus 8 in order to go to B1. Is there any questions about it? Or I can give you this more clear example. In the right side, each slot is denoting one element. in our example, because the element is 8 bytes, so each slot is 8 bytes. Let's just draw the memory by 1 byte and 1 byte. Let's see, this is the memory. And the start address is XB. We need 8 of these subslots. Right now we're drawing memory, and each slot is 1 byte. We need 8 bytes to hold the B0. 1, 2, 3, 4, 5, 6, 7, and 8. There is XB plus 1, XB plus 2. There is XB plus 7. Here we gather 8 addresses or 8 bytes. Altogether, they denote the B0. Yeah, B0 occupy 8 bytes. And if we want to look at a B1, we should start right here with B1. If we look at it right here, B1, we need to use another 8 subslots to represent B1. If we write down the starting address of it, it should be XB plus 8. Here is where XB plus 8 comes from. And this 8 happens to be the size of this element. Any questions? So the left side, we draw the memory 1 byte, 1 byte. And each byte have a unique address. And by +1, we go to the next byte, so on and so on. The right side, we draw the layout by the size of the element. Each slot in the right side is an element. For one element, it could be 4 bytes if it's integer element. It could be 8 bytes if it's a char pointer. So the size of it is dynamic, depending on what is the type of the element. The right side is a layout for the array. Each slot is one element. So the left side just explains why XB plus 8 would go to the next element from B0 to B1. That's the reason. Again, if we look at follow the right side, we have XB plus 8. We could quickly know what should be XB plus 16. Yeah, what should be the address for B2, which is XB plus 16, so on and so on. If we generalize the whole situation, it will be XB plus, we definitely should have I, and we should times the size of it, which is 8. You can try whether it is correct. If I equals to 0, we look at the first element, 0, and then it is XB. The address of it is XB. If I equals to 1, we look at the second element, then the address of it is XB plus I times E1 times 8, that is XB plus 8, right? So this is a universal equation. You can give the index of the element, and then you can quickly get what should be the address of the element. This is how we get it. Any questions? Yeah, Catherine, you give the right answer, XB plus 8I, And also, yeah, Roman, you're right. The char pointer is 8 bytes and the integer is 4 bytes. So the address for the element I would be xp plus I times 8. Feel free, if you have questions, to use microphone or chat. If you don't have questions, let's look at the third example. Let's try to do C. What should be the element size and what should be the address for element I? I will give you another 3 minutes. And you can put your answer in the chat window if you like. Okay. Do you have any ideas? So first off, what is okay? The first question is straightforward. The element is integer, and the size of it should be 8 bytes. Should be 4 bytes, right? And the question is, what is the address for element I? Okay, let's do it together. So the element size is 4 because the integer, and the start address is xc. There's no problem. We talk about for the element I, we just times the size of it because the size is 4. So we times 4, then that should be the address for element I. Any questions? Okay, let's go ahead. Finally, let's look at what is integer star star d4. Okay. Now let's look at the last guy. And we have integer star star. If you remember, when we have two stars, it's called the pointer to the pointer. And for pointer to the pointer, the starting, it is still a pointer, right? It is still a pointer. How we can understand pointer to pointer? Let's see, we have something. Integer a equals to 10. Then we have a pointer points to the address of a. Then we could have a pointer to pointer. We get the address of pointer and give it to p. So if we draw that in memory, it will be something like this. There is a, we use the memory to hold this address. And then here, let's see, the address of it is 0x110. Here's the address. And then we have another variable. We call this variable PTR. This is the pointer. And the address of it, let's assume it's 120. Okay. And because the pointer is pointing to variable a, and inside of it, we would have the address of a as the contents. Okay, let me draw this way. Erase. Okay, let's. If we have another variable PTR, we assume ADDR of it is 0x120. And in this memory place, we put the address of A inside of it, which is 110, so that as if this pointer is pointing to the variable A. And if we look into the physical memory, we put the address of A, which is 110, as a content for the variable. This is how we build a pointer, and then by having this pointer, we can find where is the variable A, and this is the pointer to the E. And if we do more, in the third example, we have the pointer to pointer. For the pointer to pointer, what it means is we have another memory location. Again, it should have its address as well. Let's say it's 0x130. In this variable, it is a pointer points to another variable. And this variable is PTR. So we put down 0x120 inside of this variable P, so that the P points to PTR. Because this is, for P, it is also a pointer. So it's just the only unique feature is it's pointing to a pointer as well. It's not pointing to an integer, char, variable like that, but it's a pointer. So we call it pointer to pointer. And the way we initialize it is to have a double star. Sometimes we use this data structure to build a list, have many layers. So it can be used in more advanced data structure. pointer to pointer. And for this pointer to pointer, could you guess what is the size of each element? Do you have an idea what is size for each element? Okay, we will give you that. The size of it is still 8 bytes, the same as a pointer. No matter it's 110 or it's 120, its address. So as long as it's address, we have 8 bytes to denote it. So for the PE, the content of it should also be 8 bytes. It's the address of the pointer, PTR. Okay, 8 bytes is the element size. And then if we summarize the address for element I, what we can do is we have the XP plus I, this is the index, times 8. Here would be the starting address of element I. Feel free if you have questions. If not, let's continue. Here is the answer. When we share the slides, you can check the answer key. Now, let's talk about the pointer arithmetic. That is when we use pointer and do the arithmetic, what that means. And here is an example. We have the integer e with elements, 10 elements. If we only write down e, what that means is the integer pointer. So when you write down, do the declaration for the integer array, and then in your C program, you put down the array's name, and the array's name would be interpreted as integer pointer. And in terms of its value, because it's an integer pointer, we need a value that telling us what is the starting address of the array. Apparently, we use XE to denote the start address of the array. And if we look at the assembly, what it usually do is move RDX to REX. So the RDX is usually the starting address of the array. So we move the starting address of the array to REX. Assume REX is where we care about the expression E. So as long as you put down E or the variable's name, the array's name would be interpreted as integer pointer. And now let's look at when we write down EI with I put inside of the bracket, what's that mean? When we write down expression like that, we are referring to one element in the array. So because it's one element, so the type of the EI would be simply integer. And when we talk about its value, we are how we interpret this expression. So the M, if you read textbook, M means memory. What inside of the bracket is the address of the memory. We talk about EI. If we look at its address, that is the ith element. We still have the XE as a starting address, plus index I times the size of each element. In our case, it's 4. So using this address, we can find the ith element, and then we use M, put this address in the bracket. We get the memory content of the address. If you look at the assembly code, it usually looks like this. RDX is the starting address of the array. RCX is the index. and the 4 is a scalar. And here is you see a parenthesis. As long as we see a parenthesis, we know it's a memory location. And the address is RDX plus RCX times 4, right? And for RDX, we see here, for the RDX, that is starting address of the array, which is XE. RCX is the index I times 4. Then we should find the address for the ith element. We have this address, and look at the memory content, and then move the memory content to RAX. So that's usually the assembly code dealing with EI. Next, let's look at E2, but we have the AND in front. And this AND, we talked about, is extracting the address of the E2. So E2, based on the previous slides, E2 is element of integer. The type of it is integer. Now we are curious about what should be the address of this element. Okay, so we talk about address of one element, and this element is integer. So we're looking at integer pointer for the type of it. And because we're looking at the address of it, let's calculate. Its index is 2, so we have XE plus 2 times the size of each element, which is 4. So the address of the element E2 should be XE plus 8. So that's how we get XE plus 8 from here. And we talk about we're extracting the address. So we use LEAQ. In this case, we just have RDX, which is the starting address of the array. In our case, is XE plus 8. 8 is the index times the 4. So we find the address of the memory and give that to RAX. We're using the LEAQ for its original purpose. Load the effective address of the memory location, and then give that address to RAX. And the assembly usually look like this. This is when we put an AND in front of E2 or EI. We are extracting the address of it. Here's something interesting. How about this pointer? We talk about if we write down E directly, it is representing an integer pointer. And if we do the arithmetic over the integer, what would happen? First of all, if you do the arithmetic, it is still integer pointer. So not change to the integer pointer. But what we should be careful is how we calculate the address. E, apparently, this is starting address of the E plus I minus 1. So the E apparently is the starting address of the array, which is XE. But when we plus I minus 1, we're not plus I minus 1 directly. This is not the case. In the C program, we're actually doing something called the pointer arithmetic. For the pointer arithmetic, the answer is XE plus I minus 1. This is apparently should stay, but at the same time, we times the size of each element. In this case, we times 4. In such case, you can see what we are trying to calculate is XE plus 4I minus 4. Something same as a value. That's the arithmetic. If you plus a number or minus a number directly over integer pointer, you should actually include the size of each element so that as a scalar, so that you can get the right results. If you look at the assembly code, it's something telling the similar story. Here, RDX is still the start address of the array, which is XE. RCX is I, and if we do them together, that is I times 4. And in front, we have -4 as well. So we just -4, so that we get the value of it and give it to the REX. Basically, it's the address of it. So when we plus I or plus number to the integer pointer, don't forget to scale the offset by the size of the element. This is called a pointer arithmetic. Here, there's another interesting one. So for the first expression, we're looking at the ith element for sure. Now we get the address of it. We get the address of it. So the whole expression would be the integer pointer. Okay. And for E, we also talk about it. For the E, should be integer pointer as well. When we minus them together, what we have is something called I. If we look at the address of EI, the address of the EI is XE plus I times 4. If we talk about E, it is XE. So you may wonder, the results should be I times 4, right? If we translate them to be the addresses, if we minus 2 addresses, and then it should be 4, I times 4. But don't forget, this is the pointer arithmetic. When we do a pointer arithmetic, we need to divide it by the size of the element. So here we need to do a size of integer, which is 4, and then we should get I as the results. So we will get I as a result. That's the difference of the index, and it's the integer type. So we just moved integer RECX with the integer I to the REX if we do this in assembly sense. Okay, so we can see here when we do a pointer arithmetic, there's always the scalar associated in the calculation process. In the previous case, if we want to plus some number, we need to scale the number with 4. And if we want to minus something, the 2 pointers minus each other, which should generate integer in our example, and the address should be divided by the size of the element as well. So this is called the pointer arithmetic. Is there any questions? Okay, if you don't have questions, let's do some examples. We talk about the pointer to the pointer. Let's take pointer to a pointer as an example. We have 4 of them. And let's see, the starting address of the pointer to the pointer is XP. And now, let me ask you this question. What is the type of P2? What is the type of P2? So let's just draw this diagram to illustrate what we mean. When we have the pointer-to-pointer array, each element is a pointer-to-pointer. Yeah, so each element, the type of it is pointer to pointer. So we've answered the first question. If we write down P2, we look at each element. For each element, the type of it is integer pointer to pointer. And for P2, if we look at P2's address, what should be the type of it? P2 is already pointer to pointer. If we look at its address, it's a pointer to pointer to pointer. If we look at P2, if we just put down P, the type of it should also be the pointer to pointer. 3 layers of pointers. Maybe you may get confused, but let's just make things easier. Let's see, we have integer pointer array. Okay, maybe this is easier example for you. If we look at each of the type, let's redo the exercise. And for P2, each of the element is a pointer, integer pointer, right? So integer pointer for the P2, and if you look at the integer pointer's address, it is pointer to pointer. And if we only look at P is the starting address of it. And by definition, it should also be the pointer to the pointer. It points to, the P points to the first element of the array. The first element is integer pointer. So P would be the pointer to the first element of the array, which is pointer. So translate in a single sentence is pointer to the pointer. If we have the P plus 3, what would happen? If we plus 3, we are doing integer arithmetic. It is due pointer to the pointer, and this time, if we look at the value of it, it should be xp, the starting address of the array, and we plus 3. 3 should scaled by the size of the element. In our case, it's a pointer, so it's 8 bytes. So we're looking at, if we P plus 3, we're looking at the if we check the fourth element of the array. And again, if we have a 2P3, get the address of it, we talk about this is already pointer to pointer, and if we minus P1, get the address of it, and then if we do the calculation, the answer should be 2. If you want to do a exact calculation, that it should be xp plus 3 times 8 minus xp plus 1 times 8. This is trying to do the subtract divided by the size of each element, which is 8. So if you do the calculation, it's going to be 2 as a result. So this example, just to give you, if we have a integer pointer array, what would be the each type if you put down P2 and put an n in front of P2? if we add a value to the pointer, what would happen? What does it mean? This is called the pointer arithmetic. Do you have any questions? Yeah, I know you guys are tired. Let me just record everything, and after class you can rewind and try to take time to learn the material. Here is an example how we can reverse engineering the whole process. In this example, you can see this is a C program. For the C program, we declare an array with unknown type with the size of the element 10. We give 1 to A0, 10 to A4, and return 0. The right side is assembly code. We want to look at assembly code and reverse engineering to determine what should be the type of the array. Let's make a guess. So if you look at the the yellow zone, we move number 1 to RBP minus 48. So we can quickly find that RBP minus 48 gonna be the start of the array, which is A0. So A0, this element, if we look at its address, it's RBP minus 48. And if we look at next one, the purple zone, we move 10 to A4. So we know A4 is RBP minus 32. This is going to be the address for it. Now we can do the arithmetic. How about we use A4 minus A0, and based on our previous arithmetic, the results gonna be 4, right? This is the pointer arithmetic if we do the calculation. And if we do an extended version, the A4, the address of it is RBP minus 32. This is the address for A4 minus the address for A0, which is RBP minus 48. This is the address for A0. We minus them together and divide it with the size of the type. Let's say the type is T. We divide it by size of type. It's gonna give us 4 as a result. It's the exact same process as here, right? We can calculate in such a way. And by solving this equation, let's look at it. So the RBP minus 32 minus RBP minus 48, the results would be 16. So we try to solve this equation. So so it would be 16 over size of T. It's gonna be 4. Then we know size of T is simply 4. Okay. By this way, we figure out this, as long as size of the data type is 4 bytes, and then the calculation would make sense. For the 4 bytes, we can come to our mind it should be an integer. That's the way we figure out the array size is integer. Here's an example how we do a reverse engineering and figure out what should be the type of the array. We just use the equations we learned from the pointer arithmetic. So we have the two addresses, and we see what's the difference between them, and then divided by the size of the element, it's gonna give you the index difference. In this case, index difference is 4. So by this way, we figure out what should be the size of the key. And then 4 bytes, that should be an integer. Any questions? Okay. Let's look at the next one. It is called nested arrays. Nested arrays is kind of special. So our array is one-dimensional, but in our mathematics, we have two-dimensional array we call the matrix. You know how the C program could denote a matrix? It turned out that we use arrays to implement matrix. Let's see, we have a matrix, that's 1, 2, 3, 4, 5, 6, 7, 8, 9. In the memory, we know how to put down index. No, how to put down vector. 1, 2, 3, no problem. 1, 2, 3. We just bring, let's see, 1, 2, 3. This is the vector. This is the matrix. For the vector, there's no question. We just put down 1, 2, 3 in continuous space. That should be fine. But the problem comes how we use one-dimensional memory space to store the two-dimensional matrix. That's a problem. And what we do is we actually store each row by row, and by this way we convert two-dimensional matrix and feed that into one-dimensional memory. So what we're going to do is we put down 4 here, 5 here, 6, and after it we look at the third row, which is 7, 8, 9. So this is one-dimensional memory. We just scan through each row of the matrix and then put that in our memory that forms on the matrix. You can see the similar thing. For the matrix, we can call it the index of it. Let's see, it is A. Then we call the first one A0, 0. And the last guy in the same row, this is the row number, 0 is the row number. The column number is 2. This is denoting number 3. You can see here, we can always store a matrix by looking at it, scanning through each row of it, and store it using the one-dimensional array. That's the way how we implement a matrix in our memory. To be generalized, so you can see what it looks like in our memory. Here is the first row, second row, third, fourth, fifth, and you can see the element of it. We put down the first element in the first row, second element in the second row, the third element in the second element in the first row, and third element in the first row as well. And again, in our example, it's integer A53. When we write down A0, A1, A2, A3, A4, they would be interpreted as integer pointer. So A0 is an integer pointer. If we only have A, let me write down here. because it's pointing to the element A00 and find its address. So A0 is integer pointer. If we look at A, it will interpret it as integer pointer to pointer, because when we talk about A, we are looking at the address of A0, and because A0 has been interpreted as integer pointer, and then we look at its address, so A is integer pointer to pointer. So if we talk about A, integer pointer to pointer, A0 is integer pointer, and if you do A00, it's simply integer. Okay, and if we look at it in the memory address, the first element starts with XA, second one XA plus 4, XA plus 8 plus 12. So you can see the step is still the size of the element, which is 4 bytes. So the step is still 4 bytes, and we can continue to do that. So here we summarize. If we look at the address A, let's see, A23. If we look at the size, look at the address of this A23, what we can have for the equation. So what we have is XA, this is the starting address of the nested array, plus L, L is the size of the data type, in our case is 4, it's an integer. C is the number of columns. The number of columns in our example is 3. 3 times I is, here is I, here is J. So I is 2 plus J is 3. If we do that all together, XA plus, you can see XA plus 36. If you look at A23, it should be XA plus 36. Or maybe we can put down A22. Okay, doesn't matter. Okay, so that's how we can find the address for A23. You just use these equations, and you can find it out. And how we can get this equation? You can just use mathematical patterns to find that. So basically, when we have the step, it's always 4 bytes, and then you need to, and then when you find the column J, you just times with times the size of the step, and when you have the row number, you need to have a bigger step in order to find the right location. So I will leave it to you how to get this equation. If you are curious, you can come to my office hours. So what is important is we still have a way to figure out what should be the address for each element. This skill is quite essential in our class. We have the memory, the giant memory, and we have some pointers, and we need to look into the memory places and find the right spot to read or write to. Here's how to do that for the nested array. Do you have any questions? Excuse me. Okay, don't have questions. Let's give a quick summary. We have 4 minutes left. So today we talk about the array, struct, and the union. Now, we haven't talked about struct and union. We talk about next class. For the array, this is a quick review of our array. We specify the type of the array and follow with the size of it. how we store array in our memory is we inside of our computer, we use continuous memory space to hold this array all together. You can see here, we give the start address to be XA. This is usually how we do the notation. XA denotes the start address of it. And then we have 10 elements in our example. And each element have the size of the type. For the integer, the size of it is 4 bytes. And then we look at when we have different array types, how we calculate the element size and how we do the element, how we find the address for the element I. Basically, in our example, we need to first figure out the size of the element, and then if we want to look at the ith element, we just times the size. For example, if it is, in our case, if it is C is the integer C6, then the element I would have address xc plus 4 times I. And also we talk about pointer arithmetic. Let's say take an example, integer E10, and E would be integer pointer. EI would be an integer. If we put an N in front, we extract the address. Again, we got an integer pointer. If we add a number to the integer pointer, this number would be scaled by the size of the element, which is 4. And if we do arithmetic between two integer pointers, and then we would divide the results, divide the address difference by the size of the type. We give an example, integer pointers array, and what is the type for each kind of expression. And also we do a reverse engineering. What is the type for this array? Basically, we follow the rules to do the arithmetic and figure out the size of the variable or size of the element. Then we can determine it's an integer in our example. And also we talk about nested arrays. For the nested array, we use one-dimensional memory to denote two-dimensional matrix. The way is to scan each rows each time so that we can have a layout like this. And when we have a layout like this, we could summarize the equation to determine what should be the address for the xaij. Okay, that will be our class today. And yeah, next class we will be in person, and I will give you more details about the schedule as well. Okay, if you have a good weekend, you guys, and thank you for attending. And if you have questions, feel free to ask after class.
Yeah, I can tell.
Thank you. Have a good weekend.